Hello everyone, welcome to another kinetic tutoring episode. Today we're looking at question 3 of set 2 of the 2023 AP Physics C Mechanics exam FRQ. So let's get straight into it. A wind turbine includes a 3-blade system that rotates about an axis through the end of each blade, as shown in figure 1. Each blade has a length of L and a mass m, with the center of mass located at a distance L over 3 from the center of rotation, axis of rotation, as shown in figure 2. And part A is asking us to find the inertia of the entire system. So the first thing we want to do is to find the inertia of one blade around its axis of rotation, which is here. And we're going to do this using the parallel axis theorem. So we have 1/18 ml squared, which is the inertia around this point. And then parallel axis theorem tells you to do m times distance moved squared, which is L over 3. So we're going to have L over 3 squared. So this will give us 1/18 ml squared plus 1/9 ml squared. 1/9 is also 2/18, so we end up with 3/18 ml squared, which is simply just 1/6 ml squared. So this is the inertia of one single blade from its axis of rotation. So if we're considering all 3 blades, we want to multiply this by 3, so we'll get 1/2 ml squared for the inertia of the entire system. Let's move on to the next part. I'm going to write the inertia of the system here. Alright, part B is asking us to calculate the time t it takes for the edge of a single blade to complete one revolution when the angular speed is 2.6 radians per second. This is pretty simple. We know that omega can be written as 2 pi over a period because it's the rotational speed and it is measured in how long it takes for one complete revolution, or 360 degrees, or 2 pi radians, to be completed. So let's rearrange this to get it in terms of t. We will get t is equal to 2 pi over omega. I'm just going to leave it as this, but if you plug it into your calculator, 2 pi is somewhere around 6.28. We're given that omega is 2.6, and when you plug this in, you will get your exact answer. Let's take a look at C. I'm going to move my camera here so you can take a good look at it. It's asking us to tell them how much energy is lost. So we know that the energy is rotational energy, which is measured in 1/2 I omega squared. This is the formula for rotational kinetic energy. So we have 1/2. Our inertia is 1/2 ml squared, where we're given the inertia, so we can just plug in that number. Once again, you can do this alone on your calculator. We're given the omega as well, 2.6 squared, and when you plug this in, you will get the initial energy. And then this energy is also going to be the change in energy, because the energy goes from this to 0. So the amount of energy dissipated is just going to be the energy you begin with. And yeah, that's all you do. So it's just going to be this simple calculation here. Let's move on to the next step. Derive an expression for the net torque exerted on the system. Alright, so we're given this equation here. I'm going to write it down. Omega initial e to negative b ot. Omega is equal to omega initial e to negative b initial t. So, and we're asked to find the net torque. So we know that net torque is I alpha, and we're given the inertia. We know the inertia, so all we need to find is the alpha. And we know that in order to go from omega to alpha, you just have to derive. And when you derive this system, you will get alpha is equal to negative b initial omega initial e to the negative b o t. There you have it. And so I alpha will be negative I b initial omega initial e to the negative b initial t. So there you have it. This is the net torque that affects the system. So let's move on to the next part. Derive an expression for the angular displacement. Now for the angular displacement, to go from this to angular displacement, which is in terms of theta, you have to integrate. So we know that omega is just d theta dt. So here we go. This would be our first step. D theta. Multiply both sides by dt. And from here we can integrate. On the left side we just get theta, and on the right side we get so there you go, there would be your answer here. And the final part is saying the three-blade system is now replaced with a second three-blade system identical to the first, except that the second three-blade system slows down according to the equation omega is equal to omega initial e to the negative bt, where omega initial is 2.6 radians, so that stays the same, and b is greater than b initial. So this new b that we have, this new constant that we have, is greater than b initial. The original angular speed function is shown. So since this is a greater number, the exponential that e is raised to is going to be changing at a faster rate, meaning that the angular speed is going to be approaching zero at a faster rate, because this is e to the negative bt power. So this is going to have a deeper slope right here, as you can see here. And what I just did is solve the last problem. Sorry guys, I didn't read it. It says on the graph in figure 4, sketch the angular speed, and as you can see, it has a faster change because this exponential is going to be decreasing more rapidly. So that's how you would go about solving that. And there you have it guys, that's how you would go about solving all of these problems. I hope this was helpful. If you have any further questions, make sure to leave them below in the comments, and I will try my best to help you guys out. And yeah, that's all I have for you guys today. Thanks for watching, and I hope to catch you again for more physics help.